All right, these are 6C notes. We're going to be looking at power functions today. So let's first start off by stating the domains in interval and set notation for the following functions. All right, so let's look at L of x, which is x squared minus 4. Well, that's a quadratic. So you should remember that the domain of a quadratic is negative infinity to positive infinity, or all reals. Okay? All right, look at m. This is 3 times the square root of x. The square root of x, well, the square root has to be positive, 0 or positive. So that means that x has to be greater than or equal to 0, or from 0 to infinity. All right, same thing with n. This is the opposite of the square root of x. X has to be 0 or higher, so x greater than or equal to 0, so 0 to infinity. All right, still a square root. So this value underneath has to be greater than or equal to 0. So let's solve for x. So the opposite of x is greater than or equal to negative 4. Divide by negative 1, which flips over your inequality. So that means x is going to have to be x less than or equal to 4, which is negative infinity to 4 in interval notation. All right, x minus 2 is a line, so that's all reals. All right, here, remember 0 can't be in the denominator. So x squared minus 16 cannot equal 0. So that means x squared equals 16 cannot equal 16, so x cannot equal plus or minus 4. So it's all reals, but x can't be negative 4 or positive 4. In interval notation, I'm going to move up here to have some room. You're going to go negative infinity to negative 4, and then negative 4 to 4, and then 4 to infinity would be in an interval notation. Because we want to skip over, so notice they're open parentheses at negative 4 and 4. So basically we're skipping over 4. So all reals but 4 and negative 4. All right, that's domains. Because what we're going to be doing today is we're going to be combining these functions and making new functions and stating their domain, or new expressions and stating their domain. All right. Now, adding and subtracting we've done before. Let's look at something that we haven't done much of. Let's look at division. So we're going to make a new polynomial, m of x over n of x. Well, this is not necessarily a polynomial because square root of x is not a polynomial, and the square roots are a polynomial. I should say function instead of polynomial. All right, m of x is 3x to the 1/2, and n of x is the opposite of x to the 1/2. Now be careful, do your domain here before you start simplifying, because look at our note. The domain of a new function consists of the x values of the domain of the original functions. Domain of a quotient does not include x values for which the function in the denominator is 0. So we have to take into fact, before we simplify this, what are the restrictions on my domain? First of all, it's a square root, so it's going to have to be positive. And because it's in the denominator, it can't be 0. So that means my domain on my new function is going to be 0 to infinity, or x greater than 0. It can't include 0 because 0 cannot be in the denominator. All right, simplify this. You're going to get 3 over negative 1, which equals to negative 3. But you're still, because you made it up of n of x and m of x, you're still restricted on the domain of those functions to begin with. All right, let's look at the next one. L of x, which is x squared minus 4, and h of x, which is x minus 2. Here again, let's do the restrictions based on this. Because this is in the denominator, x minus 2 cannot equal to 0. So that means x cannot be 2. Or in interval notation, it would be the following. All right, now let's simplify it. Let's factor x squared minus 4. All right, these are common factors, well, that's going to equal 1, so my final answer is x plus 2. Here again, make sure you do your restrictions, do your domain restrictions before you simplify. Otherwise, you're going to lose them and you're going to get the wrong answer. Okay. All right, so next we're going to look at inverses again. Now remember, an inverse relation is a relation that interchanges the input and output values of the original relation. Basically, the domain and range values are switched. So let's flash back to Unit 2. We've done this graphically already. So we want to draw the inverse of the following function. Notice this is a quadratic, and this is a function. This quadratic is a function. We want to know is the inverse of function. Okay, so remember that the reflection line is always y equals x when you do inverses. We want to pick a number of points, and then we're just going to switch the x and the y and regraph them. So the more points you pick, the easier your graph's going to be. All right, let's write the coordinates of these points. So we're going to have -2 and a half, -4, -2, -2, -1, 1, 0, 2, 1, 1, 2, -2, and 2 and a half, -4. All right, let's switch them. So our inverse is going to be -4, -2 and a half, -2, -2, 1, -1, 2, 0, 1, 1, -2, 2, and -4, 2 and a half. And we're going to graph those and connect them, and that's going to be our inverse. All right, let's do this. So -4, -2 and a half, -2, -2, 1, -1, 2, 0, 1, 1, -2, 2, and -4 and a half, 2 and a half. So let's connect those. So that's the inverse. So like I said, we did this in Unit 2. And here, notice that the vertical line test, all right, it's going to touch your line twice, so that means our inverse is not a function. That's going to come into play here in a moment when we do this algebraically. All right, so let's look at how we do it algebraically. To find the inverse algebraically, we're just going to switch the x and the y, and we're going to solve for y. So f of x is another name for y. So we're going to rewrite this as x equals 2y squared minus 1. So switch x and y, and then solve for y. So we're going to add 1, divide by 2, and since I'm solving for y, I'm going to have to take the square root. Now I'm taking a square root, so that means y is going to be equal to plus or minus the square root of x plus 1 over the square root of 2. Well, notice that this is not a function. Why? Well, the original was a quadratic, so when we graph this, the square roots, we're going to end up with something that looks similar to what we had before. So the vertical line test tested it twice, so that inverse is not a function. So that's kind of what we're going to be asking you from here on out. Is that inverse, when you're done with it, is it a function? All right, let's look at another one. All right, here again, let's switch your x and the y. Notice my restriction here. We're saying x is just less than or equal to 1. That's going to come into play in a moment. So let's switch our x and our y. So x is equal to y minus 1 squared plus 4. So subtract 4. Square root both sides. So some square rooting is going to be plus or minus the square root of x minus 4 equals to y minus 1. But let's stop for a moment. Notice my restriction. It's saying that x is less than 1. So that means I just want the negative half. So instead of doing plus or minus, I just want the minus. Why? Because of that restriction. So I'm just going to keep the minus. If it had said x greater than or equal to 1, then I would have kept the positive. And the reason we're doing this is to make the inverse also a function. All right, let's finish this up. So we're going to add 1. So 1 minus the square root of x minus 4 is equal to y. because this is a function, we can replace this with inverse function notation. So the best answer here is the inverse of x is equal to 1 minus the square root of x minus 4. Now, I only use this notation if the inverse is also a function. All right, so think about what we've done here. Okay, well, going back to this original drawing over here. By doing this, we're not taking this upper half here. We're only keeping the lower half, all right, which is going to make the inverse a function. So that's what that restriction does. When you do a plus or minus and you see that restriction, you're either going to keep the positive half or the negative half. And the whole reason for doing this is to make that inverse a function. Okay. All right, look, we got a cube. We don't have to worry about cubes, okay, because we don't need a plus or minus. So we're going to switch the x and the y. Cube root both sides, so I get the cube root of x is equal to y minus 3, and then add 3. All right, is this a function? Well, a cubic graph looks like this, right? Cube root graph looks like that, so that's a function, so that means our inverse is a function, because this is just a cube root graph that's been moved up 3. So and use inverse notation. Now you can either write this as 3 plus the cube root of x, or the cube root of x plus 3. All right, so it's commutative. But because the inverse is a function, that's why we want to use this function notation. All right, let's do one that's a little bit more algebra intensive. All right, same thing here again. This is a rational function. I know we haven't looked at these yet, but this is a function, a rational function that's coming in Unit 8. Let's switch the x and the y. All right, let's solve for y. So the first thing I'm going to have to do is cross multiply. So this is going to become x times y plus 2 equals y minus 1. All right, distribute xy plus 2x equals y minus 1. Now remember, I'm solving for y. So my next step is I want to get y's to same side. Write down these notes, because when you come back and look at something, when you have a question, you have something to look back at. So that means I'm going to subtract y, and I'm also going to subtract 2x. I get my y's on one side and my non-y's on the other side. All right, I'm solving for y, so let's factor out a y. So factor out GCF of y. And then remember, I want to get y by itself, so that means I'm going to divide by that x minus 1. Okay, so there's my final answer. And this, like I said, I know you don't know what this looks like picture-wise, but it is a function. It's a function, but what's our restriction on the domain? X cannot equal to 1, because we can't have a 0 in the denominator. All right, so those are inverses. Switch your x and y and solve for y. All right, the last thing we're going to do a little proof. It says f and g are inverse functions of each other if the following is true. If f of g of x is equal to x, and the composition g of f of x is equal to x. Now, this notation, we can also write it as f of g. Looks like fog, but it means this. It's kind of shorthand notation. You'll see it again next year in pre-calc or math analysis. This one would be g of f, and it means g of f of x. It's just what we call composition notation. All right, so we got to go both ways. So to verify this, you've got to show that this is true, that f of g of x, remember composition, so we're going to take g of x, and we're going to plug it into the x of f of x. So 5 times the cube root of x minus 5 cubed. That has to simplify to x. Let's see if it does. Well, the cube root cube just gives us x over 5, and that's just going to give us x. So that's half done. You got to show it both ways. So now we've got to do g of f of x. So we're going to take f of x, and we're going to plug it into that x in g of x. So we got the cube root of 5x to the third over 5. 5 over 5 is 1, so we got the cube root of x to the third, which just gives you x. So since they both compositions equals f, we can say that therefore we've proved that f and g are inverse functions. So it's a proof. Okay? And so like I said, if it asks you to show that one's an inverse of the other, this is what I'm asking you to do. I know you can find the inverse of one of them and show that it equals to the other one, but that's not the verification. It's method here. Remember, a lot of what we do is method. All right, if you have any questions, please make a note so we can talk about it later.